So thanks very much for the opportunity to speak at the conference, and the topic of my presentation is performance diagnosis informs efficient training program design. So today we'll be discussing the process of determining, assessing and monitoring performance qualities which are critical to the target sport. And this is an underlying principle of athlete development, because here we're determining those physiological and biomechanical aspects that dictate performance in any particular activity, assessing those and then using it for more efficient and effective training program implementation. So this process is called performance diagnosis, and it's based on the fact that any sport will have key cardiorespiratory, neuromuscular components that characterize the performance, and each sport will be specific, individual, and will be different. There will be similarities across certain sports which are similar, but certainly even activities or movements, skills within a given sport will also have key performance qualities that underlie them. So discriminating and evaluating these components, it's invaluable for athlete monitoring and program design. The process is called performance diagnosis, and it's based, as I've said, that certain measures represent specific or independent qualities of performance. So defining performance diagnosis as the process of determining an athlete's level of development of distinct strength, power, speed, endurance, and other qualities. Targeting specific performance qualities with prescribed training will result in enhanced athlete performance. Now, this is based on underlying physiological theory, and for all sports, they're going to require different performance components, or these qualities, as we call them. So in 1994, Professor Bill Kramer and I published a paper in the Strength and Conditioning Journal where we outlined the mixed methods approach to athlete development. And the reason why we wrote the paper at the time was that in the United States in particular, there was a very strong focus on the development of absolute strength, and it was certainly pervasive across the collegiate strength and conditioning environment, where coaches in the main had a lot of experience on how to make athletes bigger. So that was based on predominantly bodybuilding methodologies, and also how to make them stronger, drawing on predominantly powerlifting or maximal strength training methodologies. However, we proposed that for different sports, they're going to require different levels of these components or these qualities which would be required. And it may not be absolute size and absolute strength. And that's why we proposed this mixed methods approach. And certainly promoting, at the time, greater emphasis on power rather than maximal strength. So developing the capacity of the athlete to provide very rapid rate of force development, and also to perform with high force output even when their muscles were contracting quite quickly. So that basically is the definition of maximal power. Now, the more developed a particular component or quality, the smaller the window of adaptation. And this again relates to a very basic physiological principle of diminishing returns. And so the more developed any particular quality, then the greater the training effort has to be put in to produce even small adaptations in that component, because it's already getting closer and closer to the genetic limit of the athlete's capability. And so even large amounts of training effort only result in fairly modest improvements in that particular component. However, components which are not well developed will have a much larger window of adaptation. And so the greatest efficiency of training will be derived from targeting the components in which the athlete is most weak, not in which they have most developed. So here's just one example we presented in our paper in 1994. And this is an example for a team sport development. And we see that in this case we proposed a 5-component model in which the different components contribute to the larger window here of overall team sports performance. So this may, for example, be football. And so here we have the overall performance here, and then we have the various components that contribute to that performance. Now, I've left out other aspects of team performance here, such as in football, such as skill, for example, and team tactics and those sort of things. We're talking here about, we're limiting our discussion to actual physiological characteristics within the athlete. So in this particular model, we see that for football, of course, aerobic capacity is very, very important, but also repeat sprintability. We see that strength and power is important because the athlete has to kick, has to jump, change direction, accelerate. Overall outright sprint speed, and then change of direction and reactive agility as well. Now we see that for football, for example, we often see that the athlete is very well developed in terms of their aerobic capacity. And so they're well down the continuum here for the development of aerobic capacity. And their window, therefore, is quite small because they're getting close to their genetic capability for aerobic capacity, as an example. However, we might see that their strength and power has not been well developed. They don't have a long history of training of strength and power, and so they might be back here in terms of their genetic capability. And so the window of adaptation for strength and power is relatively large. Now we could stick with this level in terms of the model, and it would be quite reasonable to assess each of these components and then determine relative strengths and weaknesses and then train those specifically. Or we can go into more detail and delve down into a particular component. So we'll do more in-depth analysis of strength and power. So the window of maximal muscle power development, again, has several components to it. And certainly absolute strength at slow velocities is an important component here. But also strength at fast velocities, because most athletic performance is performed at speed. Yes, powerlifting, for example, the movements are relatively slow. That's necessitated because we're at the maximum force capability is the most important characteristic. So movement speed has to be slow. But most sports, and in particular team sports, expression of maximal strength in slow movements is not common. It's more likely they're going to have to express strength during more fast movements when their muscles are contracting rapidly. Maximum rate of force development, also very, very important for muscle power output overall. Capacity to use the stretch shortening cycle and reactive strength, also very, very important. And then the ability to pull all this together to coordinate all of the various muscle contractions and movements, flow of power through the kinetic chain, coordination and skill also contributes. So again, what we saw, particularly in the development of football and basketball collegiate programs in the US, the athletes in the main had fairly well developed strength at slow velocities because of the type of training they were doing. Deadlift, squat, bench press, etc. Heavy weights, and so strength at slow velocities was fairly well developed. So they're well down this continuum here. But they weren't doing much explosive work. Remember, this is in the early 90s, and so their strength and fast velocities was not well developed. And so they had a much larger window for adaptation here. And similarly, the other components as well, in general, were not well developed and could be improved. But again, the process is about determining capacity in each of these qualities. And each of these qualities can be assessed independently. and relative strengths and weaknesses determined. Now, we could delve even further to each of these, but we're getting into a fair amount of depth, probably not applicable certainly in the team sport environment, but when working with individual athletes, perhaps in athletics or swimming, there is the capacity to go into this sort of detail. And if we look at the window for maximal strength development, the various components that contribute to it, certainly a key one is muscle cross-sectional area. How large is the muscle? And that's a key determinant of how much force the muscle can produce. But it's also a factor of muscle architecture as well, and that changes quite markedly with different types of training. Stiffness of the musculotendinous unit, and then we have the neurological components contributing, motor unit recruitment and rate coding and rate of onset. And again, these can be individually trained and assessed, but we're getting into a fair level of detail here. So what is the process for determination of these key performance characteristics? Now, of course, this is essential for achieving training goals. If you don't know what characteristics are actually determining the overall performance, then how do you know which ones to train or how to train them? So various processes: biomechanical evaluation, physiological needs analysis, analysis of high-level athletes in the sport, and ongoing monitoring. So let's have a look at these in turn. Biomechanical analysis. So quantification of the force, velocity and power profile of the target movements. So this is absolutely critical, and it's quite interesting how quite often this is not actually performed, or it's done incorrectly, or the assumptions that are made about the biomechanics of particular movements in a sport are actually incorrect. So as an example, we have a look at the actual speed of contraction during various activities. And if we see that the actual movement, and this is fairly easy to measure, there's obviously many biomechanical analyses of just about every sport, and we see at the movement speed that they're actually occurring, then we can design training around that so that the actual components of the training are actually performed at speed to match what the athlete has to perform at. Or the power output, how much power they're actually producing, and then trying to mimic that during training as well. Contact times, analysis of joint and muscle involvement, the type and rate of contraction and the range of motion. Two examples here. Some work that was done, a couple of decades ago, when I was doing some consultancy work with the US Ski and Snowboard Association. And there was a paper that came out by a Japanese group showing the biomechanics of downhill skiing and indicating that predominantly it was eccentric muscle contractions, and that this was the most significant component of the downhill. And so what we did at the US Ski and Snowboard, we really started to focus on eccentric strength. We came up with various methodologies to assess maximal eccentric strength of the athletes, and then some innovative ways in which we could actually train eccentric strength. But before that, we were either having concentric only focus or a combination of your normal concentric eccentric training. Range of motion is another good example, and here we see probably off the top of my head, I think we could take cycling, for example, looking at the range of motion of the knee joint during flexion extension in the cycling action, and training specifically to that particular range of motion. Very, very important, because as we know, training at particular angles produces increases in strength and changes in the muscle architecture and the neurological activation specific to that particular point in the range. Physiological needs analysis through game analysis, the use of video, and now of course we have GPS and inertial motion measurement systems as well. So we now have access to a very large range of data which provides an understanding of the duration of the event, the intensity, the work rest ratios as well. And this is important for informing training program design again. Probably a good example I'll draw on football again. So football in the European leagues and the English leagues were some of the first to introduce GPS in actual gameplay, and the subsequent research coming from that work showing that the athletes are spending a predominant amount of time actually standing still, walking, or very slow jogging, and that's interspersed, of course, with maximal or near maximal sprints. And it was that knowledge which really changed training and preparation for the sport of football. Much less emphasis on moderate intensity continuous training, and much greater emphasis on high intensity interval training, specifically to match the training demands with the actual target sport activity. Power performance under fatigue. Again, it's one thing to produce high power output when you're fresh, and we often test the athlete when they haven't got any residual fatigue from training or from competition, but that's not the reality. Some work I'm doing at the moment with one of my PhD students, Matt Springham, based in the UK, and very interesting, the analysis of in the Champions League, and what we're seeing is that players several weeks during the year will have to play 2 matches within a single week. So what we're seeing is an accumulation of fatigue, and they still have to perform, and that power performance, may be under a fatigue state, most likely is. So again, we can assess that independently. We can fatigue the athlete, then assess how they perform under fatigue, and then implement training protocols which can actually help them to perform better. Combative sports, again, it's a whole different aspect. It's one thing to be strong and powerful and be able to move quickly, but what's the impact of repeated physical contact and impacts that are common in NFL, the Australian Football League, Rugby Union? It is a different sort of quality. It's one thing to be highly fit. It's another thing to be highly fit, but also when you're in a combative sport, you're getting constant contact, impacts, etc. There's then environmental issues, which we won't go into today, but consideration of heat, cold, and altitude, and body composition as well. How are they? How do they have to be manipulated to optimise performance? So that's a physiological needs analysis. Let's move on to analysis of high-level athletes. So this is very useful again, getting a profile of the top athletes in your squad. If they're successful, we can assume that they have the appropriate performance qualities for that particular sport. And that can then be used as benchmarks for less developed athletes, junior athletes coming into the squad, rookies, to see, what are the key qualities? I mean, what do they really have that are highly developed? You have to use some caution with this. I mean, success may be due to factors other than underlying neuromuscular and cardiorespiratory capacity. It could be due to, in a team sport, for environment, just extraordinary tactical capability, very high level of cognition and being able to track many players simultaneously, raw motivation. So there's other reasons, but in the high level of sport, elite sport today, that's highly unlikely. It would be unusual, or if not impossible, for an athlete to perform at the highest level unless they also had the underlying machinery, unless they had the underlying performance qualities. Ongoing monitoring. So this involves testing athletes before and after certain phases of training. And then we see minimal improvements. It probably indicates that that particular component is already well developed, and so it may be a relative strength of the athlete, but not necessarily so. It may be that the training program's not actually targeting that particular quality very well, or it could be that they have a foundational quality which is not well developed. Some papers that we published a couple of years ago in Medicine, Science of Sport and Exercise with Prue Cormier as the lead author. We showed that if athletes don't have underlying strength, then development of power is difficult, and concentration on power training is probably not going to be that rewarding. You have to actually build them to a certain level of strength first. and then introduce more power training to build on that foundation. And we'll have a look at an example of how to assess that momentarily. But if they produce a large improvement in a particular quality for a given training volume, then clearly that hasn't been well developed in the athlete, and they've got good capacity to improve that. So that's something to take note of, and then that can then be revisited in later training cycles. And you can then maintain the emphasis until a plateau occurs, and then of course in a periodized program cycling through other focus or foci or concentration. The next one is comparison across the squad, and we use this extensively to see how the individual ranks on a particular quality. If they're low on a particular quality relative to their peers, and that's an indication of a quality that needs greater attention. And we use frequently these plots, which are called radar plots. Some people call them spider plots, and these are just one of the graphs available in Excel. And so on this, what we do is we plot the various performance qualities that you can see here. And then the numbers that we plot are the actual Z-scores. So Z-score is how many standard deviations away from the average the particular athlete's score. And so we see that 0 here is the actual average for the squat. So if they were exactly on this line here, then they would be dead average. But we see that for this particular athlete, here for example, we can see that they're well above in certain components. So reactive strength, for example, is 2 standard deviations above the average. So statistically, they're in the top 99% of the athletes in that particular squat. So this quality, though, we see here, is actually 1 standard deviation below. So their maximum force capability during a bodyweight squat jump is quite poor. We see here that their maximum power output during a counter movement jumps here is okay. It's much higher, but it's low for squat jump. So what that indicates is that they have the capacity to use their stretch shortening cycle, but they have poor ability to rapidly switch their muscles on from a relatively resting state and to ramp their force up quickly. They can't produce a very, very powerful squat jump, or what we commonly call a concentric only jump. So looking at this plot here, we can determine the relative strengths and weaknesses of an individual athlete relative to a database of the squad, or it might be multiple squads that we're comparing them to. We could use this to compare to coach appraisal. We always map it back to the actual coach's their rating of the particular athlete and different performance capabilities. Comparing rookies versus seniors is very, very useful. You can then work what you have to actually target to bring the rookies up to the performance of the more senior players that are more developed. Comparison to past squad profiles. We do this extensively to see, well, where we're at, how are we tracking relative to the the 2016 team that won the national championships. And then individual ranking over the time, how they should actually develop as they're in your squad longer and longer, but how do they actually improve across that time period? Now, this brings us to a discussion of what's termed the test-retest cycle. And the first component of this is performance needs analysis, working out, as we've been through various processes, what's important, and then focusing on this. And quite often we see components of performance being trained or addressed, or really being having a lot of focus in training, and they may not be important to the sport. And so this is obviously wasteful of time, and concentration on certain components may actually interfere or detract from other qualities. As an example, excessive training of cardiorespiratory endurance will impact negatively on strength and power. Once the performance needs analysis is completed, we design up a testing protocol specifically to test those qualities that we have deemed to be important to the particular target activity. With the initial testing, we use that to inform the training program design. And this is important. Quite often we see that we perform some testing, a whole range of testing, which is great, but then we don't actually change the training program design, which is a bit of a waste. It's a waste of the athlete's time and effort, as well as the strength and conditioning team. So in designing this training program, it has to be targeting those qualities in which the athlete is weak, focusing on those. Now, as we know, when we work with athletes, all athletes will have activities, training drills, particular weight training activities or lifts that they like to do. And so they will generally be well developed. And so it's very much a matter of turning that around and targeting the ones which they don't like to do, because in general that will be because they're not very good at it. But only through this testing process, this performance diagnosis, will come to understand that. And then once the program's designed, implementing it and actually going through with that actual training program. And then frequent assessment here, feeding back into the training program design. How are things working? Are these components actually improving and changing, the ones that you're targeting? It's this constant test, retest cycle. Now, this frequent assessment, is unlikely to be the full test battery that you did back here. This will be the extensive one to determine strengths and weaknesses in all of the qualities, but then this follow-up here might just be targeting those qualities which you are focusing on in a particular training cycle. And then using this information from the testing, the training program and the frequent assessment to inform the coach and the athlete and the sports scientist that you're working with, to educate them, provide information about how you're actually changing these strength qualities as a strength and conditioning specialist. So I want to move on, given the limited time we have, and just give a very snapshots of key performance qualities that we would assess as example for a team sport athlete, such as football, American football, or rugby league, rugby union, hockey, and how they would be assessed, the sort of parameters that we examine are there, and giving some examples. Now, first off, we'll talk about force measurement, and this is now used extensively, and one of the main reasons is that single-axis force platforms are now readily available. They're much less expensive and easier to use. They're more portable than the typical biomechanical triaxial force platforms. Triaxial force platforms generally used for biomechanical analysis, really overkill in the strength and conditioning field, because the single-axis performance platforms only measure vertical force, or force perpendicular to the plate surface. And from that you can determine vertical force, impulse, you can predict velocity, displacement, power output, you can do measures of musculotendinous stiffness, rate of force development and power development. And you can see that each of these qualities hark back to those window of adaptation model that I presented earlier. So a great deal of what I presented in that model can be assessed using a single force platform. We can also assess symmetry, which is also very important, left to right symmetry, in particular to enhance performance. If there is great difference between the left and right, then the performance will be hampered, but also to manage injury risk. Too much of an imbalance can enhance injury risk, and then also in rehabilitation to track an athlete coming back and making return to play decisions. And this can be assessed with force plates using both dual or single force platforms. There's both dual force platform systems now requiring 2 force platforms, each giving a single force measure, and so we can separate out left and right, but also single force platforms that provide 4 force signals can also equally measure quite validly left to right balance, simply because of the shift in the center of pressure between the left and the right. So the sorts of measurements that we can do: maximal strength, and this is obviously critical for a wide range of sports, just about every sport. I can't think of too many where maximal strength is not important to some degree. And this can be measured in a variety of ways. It can be measured with limited equipment and doesn't need force platforms. It can be measured just using free weight equipment, or in this case using a Smith machine and a 1RM test. And it can be measured using submaximal tests of 6RM or 10RM, and then using that to predict 1RM. I'm not terribly in favour of that. I think that a 1RM test is a lot safer. It's quicker to do. It doesn't fatigue the athlete. They only have to lift the weight for 1 repetition per test. They either lift it or they don't. when you're performing multiple RM maximal tests, then all you're using, if you're doing a 10 RM test, you're just using 8 or 9 repetitions to fatigue the athlete to the point where the 10th repetition is a 1 RM. And so, you know, I've observed that in doing this many thousands of times with athletes, that it's under those multiple RM tests that their fatigue starts to set in and their form starts to be compromised, and I believe they're at higher risk. We've performed thousands, if not, well, be tens of thousands of 1 RM tests on a whole range of athletes from juniors through to elite. Myself, I've performed thousands of tests in elderly people, including cancer patients, and we've had no problem with it. But if the coach says, look, you're not doing 1 RM, well, you've got to live with that. And so you have to consider whether you'll do a 6 RM or a 10 RM test. You can also determine the isometric maximum, and this is being used more and more, particularly with the ready availability of force platforms, and can be tested here. You can see examples on the force platform in an isometric mid-thigh pull position. Can be tested here. We've got an example for an isometric squat here as well, and just about any movement can be set up on a force platform to test isometrically. Now with this, we measure the maximum force they produce, force maximum divided by body weight, so their force output in body weights, for example, a squat of a maximum isometric squat of 2 body weights, for example. And then in isometric tests, you can get measures of maximum rate of force development, so how quickly can the athlete actually ramp up the force, increase it up to a peak. Now, with a dual plate systems or with single plate systems, you can also look at changes in force output between the left and the right. So the athlete standing on the force plate here, we can determine when they perform a maximal effort, their dominant side will actually produce obviously more force. And we can see with the single plate system here, we can see that shift in force where there's more force being registered on the right side, for example. The 2 right side load cells then is registered on the 2 left side load cells, and get a measure of symmetry there as well. Increasingly, we're seeing the use of the isometric mid-thigh pull, and there's good reason for that. There's strong correlation between the isometric mid-thigh pull and the 1 RM squat. You can see the correlation coefficient there is very, very high. And this research goes back to Stone, Professor Stone's work, Professor McGuigan's work as well. You can see those papers there. It has high reliability in a whole range of populations. For peak force, about 0.96, a CV coefficient of variation is less than 5%. So it's a very, very reliable measure. And again, we've tested tens of thousands of athletes in the isometric mid-thigh pull on a force platform, right through from junior gymnasts right through to weightlifters, powerlifters, and again we find that it's relatively safe. The isometric mid-thigh pull position is a very natural position, so you know, even people who haven't done deadlift, for example, before, or weightlifting before, you know, are quite comfortable with this position. It's a very natural way to actually lift anything, and very useful testing large numbers of athletes very quickly and very efficiently, and on occasions, and including in Malaysia, you know, we've been there and testing, you know, 100, 150 athletes over a couple of days, whilst we're also testing sprint speed and a whole range of other things as well. So we'll just have a look at an isometric mid-thigh pull. So I won't do one for you as a demonstration because I'm in my home office. But what we will do is just have a look at the analysis of an isometric mid-thigh pull. And so we'll open up. We've got some data here previously collected, just so I can show you some of the measures from this. Isometric mid-thigh pull is here. And so we can see this here. This is the typical isometric mid-thigh pull data set that you would see. The athlete starts here at this point around here, where you can set the start of that particular movement. And then the instruction is to pull as hard and as fast as you can, and to ramp up the force as quickly as possible up to a peak. And the peak occurs here. You can see it's what's about 1,572 newtons of force that they produce, and a whole range of parameters then calculated from that. The key sort of parameters that we're looking at are the peak force that they're producing, and then other measures of the maximum rate of force development here, and then impulse measures as well. So how much impulse are they producing at various time points through the actual movement. The actual time to peak force is important. You can see there's 1.182 seconds. So how long did they take? Again, that's a very important measure to see how quickly they can actually ramp up to that actual point. So there's a whole range of measures that could be determined, a whole lot of detail to go into that, but we'll keep moving with the presentation. So if I was, I'll just pause that for a moment, but if I was told by the coach, look, you can only measure one thing, and if it was for most team sports, and certainly any track and field, any event which involves, you know, very high powerful movements, I'd probably perform a strength test. That'd be, you know, I mean, it'd be unusual that they say you can only perform one test, but just getting that overall test of strength, and that's why the isometric mid-thigh pull test is quite useful, because it is a bit of a whole body test of strength, but it gives you a bit of a barometer as to where the athlete is at and how well developed they are. But certainly for any ground-based sport, in particular where there was any amount of jumping, sprint acceleration, change of direction, the next test which I would implement would be a counter movement jump. And the counter movement jump here performed on a force platform, and you can see we've actually got a bar across their shoulders, and we're tracking using a linear potentiometer. We're actually tracking their movement here in the vertical plane. For force plates today, really they're pretty good at actually estimating the velocity and the displacement of the athlete. We'll see an example in a moment. But recording the force here, we can get the reaction force, we can calculate jump height, peak velocity, power output, and then a whole swag of other measures which are very indicative of, in this case, the leg extensor qualities. And so these leg extensor qualities apply, as I say, to any sport involving vertical jump, sprint acceleration, change of direction, because it all involves that triple extension of the hip, knees, and ankles. So let's have a look at an example of a counter movement jump. So here what we're going to do is actually calculate the, just one moment to set it all up. So here we have a typical counter movement jump, and just zoom in a little bit so you can see it a little bit clearer. So this is typical counter movement jump here, and we see the start of the movement here, the force. This is the total force, and this is the left to right force measured using a single force platform. And the system automatically finds the various phases. So here we have the eccentric phase in red. We then have in green is the concentric phase, and then in yellow is the flight phase. And so it's very instructive to see in particular the profile of the force here, how it changes, the peak velocity that they produce, which you can see here, it's about 2.63 meters per second, not a terribly great jump. A good jump will be 3 meters per second or better that we can observe there. So from there, if we have a look at the actual results here, so the types of measures that we get out from a counter movement jump are such things as their peak force output, their peak force per kilogram of body weight, their peak power, and their peak power per kilogram of body weight. So that power to weight ratio, of course, very, very important. We can see here 79 watts per kilogram. Some other measures you can see as for a counter movement jump, there's many measures that can be determined, but some key ones which have proven to be very predictive or indicative of performance. This one here, flight to contraction ratio. We use this extensively in our strength diagnosis, in particular with team athletes. It's quick and easy to measure, and it's the ratio of their flight time divided by the sum of the eccentric and concentric time. And this flight to contraction ratio, in several papers by one of my past PhD students, now full professor, Stuart Cormack. And what he showed was that this flight to contraction ratio is very indicative of neuromuscular readiness to train, very indicative of residual fatigue following training or following games. This was in AFL research that we had completed. But also the analysis can also be done on symmetry as well, and we can look at the ratio between peak force, left to right, minimum force, so how much did they unweight? So again, they may not have much difference in terms of the peak force, and you can see the peak force is not terribly much difference here. If we have a look at the actual symmetry measurement here, we can see it's only about 3% at this peak force point here. But then if we move across to the minimum force here, at this point, it's about 19% difference. So when they're unweighting, how much they drop their actual force is quite different between their left and right through there. And then during the concentric phase, again, you can see a considerable difference left to right, where they're favouring, in this case, the left leg. Much lower force production on the right side. So with that, you can complete quite a detailed analysis of the counter movement jump. What we're doing a lot now is looking at the eccentric phase in detail, because your more explosive, more reactive athlete will have better capability. And again, we demonstrated that quite well in the papers by Cormy from her PhD. And what we saw was that athletes, as they were trained in explosive jump squats, they actually improved their eccentric phase. They became better able to use the eccentric phase to produce greater force and impulse during the concentric phase. And that was a very important training adaptation. And so we can see here, if we have a look at the eccentric phase from here through to here, this phase can be broken down into the various components of the unloading time, so the unweighting, then the yielding time, where they're still actually descending, but they're actually slowing the descent, rate of descent of the centre of gravity, and then the braking time, where they're slowing themselves here and actually reversing and starting to come back to a zero velocity and to a stop at the changeover from eccentric to concentric. And we can break that down then in terms of the time of each of these phases. But also what we're using extensively is the rate of force development during those eccentric subphases. So, for example, during the braking phase here, the rate of force development on average is about 8,468 newtons per second. So again, these measures tell us a lot about how the athlete is using the eccentric phase to produce a high impulse in the concentric phase. So we'll keep moving. We may have to skip over this one because I'm just conscious of the time is going quite quickly. And the something that we've been using, this is work done by, led by Professor Mike McGuigan, and use of what we term the eccentric utilisation ratio. And during this, it's a comparison of a concentric only jump with a counter movement jump to see how well the athlete can use the stretch shortening cycle. But it's also an indication of, in athletes which rely heavily on concentric only movements, for example, divers, swimmers, there's very little capacity in the start or even in the tumble turn for a swimmer to have a very high eccentric loading. It's not available to them. So it's very important that they have good concentric only power production. So we'll have a look at a concentric only jump, because this is another common test that we use. We generally wouldn't do it with a reactive type athlete, so a ground-based athlete, unless, for example, in volleyball, where quite often the athlete will have to accelerate from a crouched position and or in NFL, where quite often the athlete will have to, or rugby union, where they have to provide a very rapid force development, but from an already crouched position. And so let's have a look at what I think I've got an example here of a concentric only jump. So let me just balance this up firstly. So here we have a concentric only jump, and I'll just zoom in on it so it's a bit easier to see. Now, in this particular jump here, what it involves is the athlete starts from a crouch position here. So the depth of generally selected, let them self-select. What I do in testing the athletes is I try not to interfere too much with what they naturally do. So I don't place too many constraints. In research, yes, you do. What exact knee angle, what depth. In general athlete support and service, I generally don't. I let them, I just say do a counter movement jump. If they do something strange, then I'll offer some technique advice, but normally I just let them do what they do. So here we have the force, the total force here. Now the athlete is crouched down, holding it. There's a slight dip here. I'd probably let this one go though. And then they accelerate upwards to a peak force here. And so we analyse this again. One of the key parameters I look for is this peak force, which in this case is 1,821 or 22 newtons. Now, that is a very useful measure because it determines what peak force the athlete can get to in a concentric only muscle contraction. And so that does tell us a lot. And interesting, some work done a few decades ago at the Australian Institute of Sport. And what they found was in elite rowers that measuring a whole range of performance qualities, this actual measure here was one of the most predictive of on-water rowing performance. And if you think about rowing, there's not a great eccentric component to it. You don't say you're loading up the muscles with body weight because you're horizontal, and so you don't have much capacity to really load up eccentrically the system. And so it becomes very critical as a performance characteristic how much force you can produce in a predominantly concentric only push through the rowing cycle. And so interestingly, this was determined to be highly predictive there. So that's a concentric only jump. Now this eccentric utilisation ratio, which we don't have time to go through at the moment, but it's just the ratio of this force here, 1,822 newtons, divided by, and we'll just go back to a counter movement jump in the same athlete, this peak force here, which is the peak force during a counter movement jump. So that ratio is the eccentric utilisation ratio. And again, very, very useful for determining how well they can use that additional eccentric stretch to enhance their concentric performance. So the next parameter I'd like to talk about is the dynamic strength deficit. And we reported this for the first time in a paper by Dr. Young led this actually as one of our research students, and Kieran Young. And we published this back in 2015. But we're finding it ever since over the subsequent 5 or 6 years to be a very, very useful measure in working with our athletes. Now, quite fairly easy to determine with a force platform is the determination of the peak force during a bodyweight counter movement jump. Now, we just went through that process of that peak force that they attain. But then measuring the peak force during an isometric squat. Well, you can use a dynamic squat. We tend to use an isometric squat. And the DSD is just the ratio of this ballistic peak force or counter movement peak force divided by the isometric peak force or squat peak force. And that gives you this dynamic strength deficit. So how do we interpret this? So If the DSD is low and the athlete is not terribly strong, so if this peak force is not that high, then the training intervention is obviously they have to develop maximal strength through maximal strength training. That's what's recommended. If the DSD is low, but they have adequate strength, what it means is that they're strong enough here, but this peak ballistic force is not very high. So they have the adequate strength, but they can't use it ballistically. And so ballistic strength training is recommended. So plyometrics, ballistic strength training using, weighted counter movement jumps, squat jumps with weights, etc. If the DSD is high, what that means is that their ballistic peak force is relatively high compared to the isometric, and so now they have the ability to utilise their peak force generating capabilities in a dynamic manner. And now we cycle back in our periodised model to more maximal strength training. And so we found this quite a useful measure or quality. Won't go through the limitations of time. I won't go through the actual demonstration of how we would actually determine it. But as you can see from the previous analysis we've done, that it's fairly easy to do just based off your force plate data. Next test that I would do, particularly for, again, ground-based athletes, particularly jumpers, basketball, volleyball, many of your track and field athletes, is a loaded jump squat. And with this, we're jumping on a force platform. We may or may not use a linear potentiometer to track the bar movement here. And we measure the bar and the force and the bar kinematics, calculating height of jump, velocity, force, power output, impulse, etc. Now, this is very instructive. Many athletes in the squad will be able to perform quite an effective counter movement jump with just body weight. But it's a very interesting differentiator when you add additional weight. Some athletes, they'll go fine and they'll be able to produce still quite high power output. Your lesser developed athletes, what you may observe is that it will bury them. They won't be able to cope with the additional weight, and that will differentiate them better than just a body weight counter movement jump. You can also test the athletes with a range of weights across the concentric spectrum. So test them with 30, 55, 80% of 1RM, for example. Or you might test them with absolute loads, with additional 20, 40, 60 kilos. It depends. Obviously, for a little gymnast who only weighs 40 kilos, then 20 kilos or even 10 kilo bar might be sufficient to differentiate them. For very strong athletes, you might use much higher than 60 kilos. Certainly in some work that I did with Dan Baker, some of the athletes that he was testing in rugby league, they're very, very strong. And of course, you can also relate it back to what loads they have to manipulate in their sport. Now, in rugby league, for example, if you have a 110 kilogram front row forward that you've got to actually tackle and bring to the ground, and that's the load you have to manipulate. And so Dan Baker was actually testing athletes using jump squats using 100 kilos or more. You can use it to determine the optimal load for power production, and this is something that some work that Greg Wilson and I did, back in the 80s, early 90s, determining the optimal load. So what you will see is as you increase the load, the actual power output will increase to a certain point, and then it will actually decrease. Now, there's a very strong biomechanical and physiological rationale that athletes should train at the load that optimizes their power output. And so you can use this test, determine what their optimal load is, and then use that in parts of their training. Not all their training, of course, but in parts of their power training. So moving on from here to have a look at drop jumps. And look, I'll point out that we're looking here predominantly at lower body tests, just due to the limitations of time for the presentation, but most, if not all, of these tests can also be translated to upper body movements, whether they be pulling movements or pushing movements, such as bench throws or dynamic push-ups to the upper body. But let's have a look at drop jumps now, in this case testing the reactive strength of the lower bodies. And here we have the athlete dropping off a height here, onto a force platform. and jumping. Now the instructions are that we want you to land, spend as little time as you can on the plate, but jump as high as you can. We then look at the force output they produce here and also the flight time, or if you have a position transducer here, and you can see in this case the position transducer is attached from above, so we can measure how high they're jumping. And then we can determine a whole range of parameters, including flight time, contact time, peak force, etc. We can test them at various drop heights, and this, for example, might be 30, 45, 60 and 75 centimetres. It depends again on the athlete. For a swimmer, you wouldn't do this test at all because reactive strength is meaningless for them. For a volleyball player, this is an elite volleyball player here, then you test them at perhaps even higher drop heights than this because these are highly reactive athletes. Similarly, triple jumpers, long jumpers, high jumpers, very reactive athletes. So you may test them at actually 1 or even 1.2 metres of drop height. So we'll take the athlete up now, and this time they're dropping from 80 centimetres. Again, an elite volleyball player, and you'll note they're not really inhibited. They still produce a very, very nice jump here because this is a highly reactive athlete. What we're trying to do by dropping them from higher and higher heights is determine the height at which the forces going through the musculotendinous system of the lower body actually triggers the Golgi tendon organ reflex, and that produces inhibition of the muscles, so they then don't jump as high. Again, this is very, very useful. We can determine the reactive strength index, which is the flight to contact time, and determine the best drop height. So the best drop height, we can see here, this is a plot of jump height versus drop height. And we can see here, this is a very non-reactive athlete. Their best drop height is actually a counter movement jump, so a drop height of 0. But then when you drop them from increasing heights, their actual jump height gets worse. A good athlete will produce a better jump height when you give them more stretch, when you provide them with greater preloading through dropping them off a box. And you can see here their optimal drop height is 30 centimetres. As soon as you go to a higher height, they get some inhibition here and they can't jump as high. Now this is very useful because you can use this as the drop height to train them for, drop them from in your plyometric training. What you should see with a training phase in your periodized cycle which has emphasis on improving reactive strength, you should see that all of the jump heights should increase at each drop height, but also you should observe that the optimal drop height actually moves to the right. So now it's from 45 centimetres. So again, very useful methodology to plan your plyometric training where you're going through a periodized cycle trying to increase reactive strength. Again, I won't go through an example here of testing drop jump performance and determining the reactive strength index just through the constraints of time. So moving on from here, I'll just spend a moment just talking about some other measures that we use frequently, and that's the assessment of balance, stability, symmetry and functional movement capability. Again, we generally do these tests using a force platform, and we measure the vertical ground reaction forces and then track what's termed the centre of pressure. So with force platforms that have 4 load cells, measuring the force at each corner of the plate, we can use that information to track the centre of pressure over the plate. This tells us a lot about the athlete's balance and stability, their left to right symmetry, and also their anterior posterior or front to back shift in their centre of pressure as well. And this can be done for both the upper and the lower body. So we have an example here. This is an example of the trace of the centre of pressure of an athlete. Here, in this case, they're performing just a straight body weight squat. And we can see how the centre of pressure actually wanders over the surface of the plate here. And this tells us a lot, not just the area over which they move, but also the direction in the anterior posterior, front to back, and medial lateral or left to right as well. We also perform similar tests, functional tests, where we drop them off a height here, have them land, and this was a test that I developed in a program led by Jeremy Shepherd, Dr. Jeremy Shepherd, when he was at the Surfing Australia. their centre of their high performance centre there on the east coast of Australia. And we looked at a test here where the athlete dropped down and landed, and then we'd used the force data to determine how quickly they could actually stabilise their force. And we found that that would separate out your elite athletes from your sub-elite surfing athletes. And the same thing applies now. Jeremy's using those similar tests with ski athletes because he's now working for Canada Ski and Snowboard. So how to express the information, and this is probably one of the most important aspects of the whole performance diagnosis process, is how well do you feed it and how timely do you feed it back. The problem is it's often done poorly or not done at all. Quite often, unfortunately, and I've been as guilty of this as anyone, is that we give some preliminary measures out to the athlete of how high do they jump, but we don't give them much more detail than that. Now, we are getting a lot better in this, and in part it's because the systems which allow us and support us to give feedback are getting a lot better. It must be complete though, it must be valid and reliable. Many times in the past I've reported values back to an athlete which were just silly, and that causes the athlete and the coach to really lose faith in you as a strength and conditioning specialist. You must report data which has been, where the tests have been done properly, where in the research literature they've been demonstrated to actually measure what they're supposed to measure, that they're indicative of the underlying quality. You know, I won't pick out any particular parameters, but in the past, you know, we've had various measures come up, and they're not actually reflecting what the underlying quality is, and that's a problem because that measure and how it's calculated isn't conforming to proper biomechanical principles. It must be easily accessed. Preferably it will be web-based, so the athlete and coach can access it from anywhere at any time. It has to be secure and confidential. The athlete and coach must have confidence that their data is not going to be shared outside of your squad or your training environment. It's important to provide research, feedback, education for the athletes and the coaches as well. Identifying these relative weaknesses and strengths, and I hope in going through this presentation you've got an understanding of how we can assess the various strengths and weaknesses, and then how training might be changed or altered or focus changed to really address those weaknesses, because the greatest improvement, as I've said, and I'll just reiterate it, will be achieved when you address those weaknesses where they've got the greatest window for adaptation, and the overall sports performance will improve, so long as you actually adjust the training program accordingly. Coming back to these profile of strength qualities, and I won't spend too much time on this, but again, we're using extensively these graphics to show as much information as possible in a clear manner. You know, you don't want to push out a whole lot of spreadsheets and thousands of numbers to the athlete and coach. It's just too much. You know, you need to try and compress it down. And again, the modern systems do this very, very nicely, particularly the web-based systems. So we have here, it's just one example, an athlete that's you know, fairly well-rounded. So we use this graph again. You know, the graph that you see here, there's no clear weaknesses or strengths, although we see here back in November they had a bit of a problem here, and that's well demonstrated, but that's been addressed 12 or 13 months later. You can see that's been corrected. For a poor athlete, we can see again this plot. They're quite good on a counter movement body weight jump, but every other parameter is well below the average, which is the zero line here. So here's an athlete that needs a lot of work, and these graphics show very clearly to the athlete what you're trying to change and why. So what to look for? Deficiencies in a key quality, that's an obvious one. A lack of progression of a target quality. If you're implementing something to, for example, improve reactive strength, and you're not seeing an improvement in that drop jump performance and their reactive strength index, it's a problem. Either there's a foundational element which is not well developed, it might be maximal strength, or your training program's got some issue with it. A sudden decline in a strength quality might indicate accumulating fatigue or a niggling injury which is coming on, or it might indicate the athlete's not recovering well from competition or from training. Excessive imbalances left to right. Many sports will induce imbalance and asymmetries, and that's got to be taken into consideration, but most sports the athletes should be relatively symmetrical left to right. an excessive agonist-antagonist imbalance. We haven't had time to go into the assessment of that, but there's many ways isometrically, both with specific isometric testing rigs, but also with force plates, by which you can actually test isolated single joint in an isometric movement, or lack of movement, in an isometric fashion, relative agonist and antagonist ratios, so hamstrings to quadriceps, for example, hip flexors to hip extensors. Real-time performance feedback, and we're seeing this used extensively now. I think trying to get to immediacy, where the athlete receives this information as they actually train or as they're being tested. The closer, and this has been demonstrated in motor control research for decades, but the closer in time the feedback is provided regarding the performance, the better it is internalised, and the better the athlete is able to adjust their technique to improve their performance. So just giving an example here, this is off a force platform here. So the athlete's getting ready for a jump. They perform the jump, they receive a tone, which is like a ding. When they hit the target is set at 2 meters per second here. When they get over it, they get a green bar. This is the actual target here, target here, line here. This is their actual performance there. So they've got 3 trials they've competed here. This is the actual jump data down here and their symmetry over here. And then you can see on their 4th jump, they've missed the target. Their 1.948 target was 3. So that immediate information provided visually to the athlete. What we do is we place headphones on the athlete, or they put their ear pods in or whatever, so they can hear the signals. That high quality of feedback is highly motivating for the athlete, but it also allows you to give coaching cues for them to consciously or subconsciously alter their technique to maximise the performance. In this case, it's the actual peak velocity. But in other cases, we may feedback minimum velocity, how quickly they're dipping, or we may feedback peak force or peak power to the athlete. So where are we heading in the future? So the next steps are, I think, ubiquitous online data collection. We're pretty close there now. We're seeing instrumentation of a wide range of equipment, predominantly wireless these days. Real-time performance feedback and reporting. I've just shown you an example of that. It needs to be web-based reporting and support. Field monitoring. The athletes shouldn't have to come into a lab. It should be done on the weight room floor wherever possible, or out on the actual court, or out in the field. So it's where they're actually working and training. Building in education, and again, we're finding this is very, very important. So the athlete understands what you're doing. In particular, the head coach understands what you're doing and why it's important. And, you know, making it accurate is very important as well, not giving garbage data back, because that really causes them to lose faith in what you're doing in the strength and conditioning, strength and conditioning group. Based on science, you know, you need for each of these measures to, you know, if the coach comes and says, what's this measure? I've never heard of it. You say, oh, here's a paper published in Journal of Strength and Conditioning. You know, this is an accurate measure. It reflects performance. It reflects this particular quality. We're getting much better, I think, in the future now and in the future, data analytics and how this is actually done. And particularly with high-performance computing, we're seeing the implementation of machine learning, artificial intelligence for the analysis of performance, the generation of important diagnostics as well. And this is really coming together quite quickly. And it's you know, making the power of performance diagnosis and then training program design, you know, much quicker and much more effective. So, look, that was a really super fast run through, and I believe I've gone over time, but look, thank you very much. Again, I want to thank ISN for the opportunity to speak, and thank you very much, and I hope that we have the opportunity to receive questions. Thank you.